Hi, I'm pleased to present our TMLR paper, IMEX-Reg, Implicit-Explicit Regularization in the function space for continual learning. Deep neural networks have always found it hard to learn sequentially due to a phenomenon called catastrophic forgetting. Catastrophic forgetting accentuates the loss of prior information when learning a new task. That is, in the worst case, previously acquired information is completely forgotten. Catastrophic forgetting can be mitigated in several different ways, including replaying previous task samples alongside current task samples as in experience rehearsal, or complete or partial isolation of task-specific parameters, or even by restricting weight changes. Experience rehearsal has been quite effective in mitigating catastrophic forgetting. In fact, the performance correlates with the buffer size. However, this poses a problem. In instances where the buffer size is limited, deep neural networks tend to suffer from several shortcomings such as overfitting, prior information loss, and representation drift. Over the years, regularization has been regarded as an antidote for overfitting in deep neural networks. Regularization can either be implicit, where there is no additional constraint or a learning objective, or explicit, where an additional regularizer constrains either the weights or the underlying function. To this end, we propose IMEX-Reg, a rehearsal-based continual learning approach that entails both implicit and explicit regularization to mitigate overfitting in continual learning. There are three major components in IMEX-Reg. We leverage contrastive representation learning as an auxiliary task, essentially working as an implicit regularizer. We also employ consistency regularization, that is enforcing consistency in the outputs of previous task samples through an exponential moving average of the weights. In addition, we propose a novel regularization loss to guide the classifier towards the activation correlations in the unit hypersphere of the contrastive representation learning. With these three loss components in place, IMEX-Reg mitigates overfitting and produces superior performance over other continual learning approaches. We compare and contrast with several rehearsal-based methods in different continual learning benchmarks. As can be seen, IMEX-Reg achieves the best performance in the majority of the continual learning benchmarks. We also provide an ablation study to uncover the contribution of different components in IMEX-Reg. Each of the proposed components add an additional value, thereby improving the performance across tasks. In the figure below, we provide the stability-plasticity trade-off across three different continual learning benchmarks. IMEX-Reg produces a better trade-off between stability and plasticity, thereby resulting in better performance. Due to a plethora of regularizers, IMEX-Reg is robust to both adversarial and natural corruptions. Such a strong robustness is handy in continual learning when exposed to real-world scenarios. To mitigate overfitting in continual learning, we proposed IMEX-Reg, a two-pronged implicit-explicit regularization approach entailing hard parameter isolation, hard parameter sharing, and explicit regularization in the function space. IMEX-Reg effectively reduces overfitting and is more robust to adversarial and natural corruptions. IMEX-Reg also mitigates task recency bias to a great extent. For any further questions, please get in touch. Thank you.